Okay, now we get into the much harder part. And this is what a proportional odds model is. It's also called a cumulative logits model. It's a little complicated. So I try to break it down into steps so they can see exactly what the model is all about. And that model turns out to be, consists of, first of all, doing some individual logistic regressions. You do 8 individual logistic regressions. Logistic regression applies to a binary variable. So I have to have one a response which has only 2 values. So what I do is introduce an indicator variable, which is 1 if the rating is equal to or less than 1, 0 if it's 2 or more. So that gives me my indicator variable. So now what I'm going to do is use logistic regression to predict the proportion of ratings that are 1 or bigger than 1. It says the log of the probability that y is equal to or less than 1 over 1 minus the probability that y is equal to or less than 1 is a constant plus a coefficient of u plus a coefficient of u squared. So then you can plug in your fat level and get predicted probabilities of a rating equal to 1 or bigger than 1. So that's the first logistic regression.
Okay.
We get 3 coefficients there. You know, the estimates in that column, just below the middle on page 6, those are the coefficients in this quadratic logistic regression model. For the second logistic regression model, now I'm going to predict a fitted model which predicts the probability that the rating is equal to or less than 2. The first one was the rating equal to or less than 1. Now I'm going to fit a model which gives me an estimated probability that the rating is 2 or less versus more than 2. And so I introduce an indicator variable, which is 1 if the rating is 2 or less, and 0 if it's 3 or more. Now I've got my indicator variable. I do my logistic regression, and I get the model, fitted model, and I just continue doing that. Third one, and call it Z3, is 1 if the rating is 3 or less, and 0 if it's more than 3. And I just keep going until I get up to 8. The last one I run, Z8, is an indicator variable, which is 1 if the rating is 8 or less, and 0 if the rating is 9. So we end up with 8 logistic regressions. Now what do we do with those? We don't need any of them in actual fact. Okay, don't need any of them. But I want the students to see what's going on here. I say, well, let's summarize what we did here. So the models are all written out. Each one of these has an intercept, has a coefficient of u, and a coefficient of u squared. Now I can tell them what the proportional odds model is, the polytomous, which is a polytomous example of a polytomous logistic regression. That model assumes that all these coefficients of the u terms and the u squared terms are equal. And if you look at those, if I look at the u's, well, I say, those smallest one is what, 27, the largest one is 42. Do those look like they're all about equal? Well, in order to answer that question, you've got to know something about standard deviations. How much variability is there present? Well, if I look at the standard deviation of the U-term, for example, the one at the top of it, standard error is 12.579. And roughly a rule of thumb is go 2 standard deviations up or down. That's about 25. So that says, well, if I go 25 up from 31, 25 down, any of those values would be reasonable. Well, that's well within the range of all of these u's. And similarly, we assume all of the u squared coefficients are equal. Well, they're all negative, but their variability is much greater. The smallest is like 88, the largest is 152. That's a pretty big spread. But look at the standard errors. Just for this last one, it's almost 38. You double that, you get 76. Those are all within range. Well, that's just eyeballing it. I mean, I think what I saw in your reaction is what most students would say. They don't look, that doesn't look reasonable to assume they're all equal. But we can take that variability into account and perform a test, a statistical test, and that's what's called the proportional odds test. If I skip ahead, that's an assumption. That's what the proportional thing is. It assumes that those are equal. Well, on page 11, there's a thing called the score test for the proportional odds assumption. The p-value of that test is 0.4173. We would reject that assumption if that were less than 0.05. So this score test says that's a very reasonable assumption. So that means that you should now trust this model, that it's a valid, so to speak, valid model. You have evidence that your assumptions are satisfied, and you can proceed and fit that model. Well, it's just done naturally. It's part of the fitting of the model. Remember what we did with analysis of covariance? There we assume that we make an assumption there's no interaction between a covariate and the factor. And if that, I mean, that's what you assume. I mean, in analysis of covariance, you assume that you got a regression on each level of your factor, and the lines are parallel. Well, that's all this is. That this is exactly like analysis of covariance. And in fact, there's something else that I could do, but I didn't do. We could plot these 8 models, and you'd see a straight line. They'd all be parallel. We could show this on what's called the logit scale. When we take the log, that's a logit scale. And then we could put it in terms of fitted probabilities, which will be curvilinear. And now we'd see curves
that are parallel.
Right. And you don't see it that often either in analysis covariance, where you fit a quadratic model